We introduced the Bounded Deformation Tree, or BD tree, a wrapped bounding sphere hierarchy capable of output-sensitive collision detection with deformable models at costs comparable to collision detection with rigid models. The BD tree is extremely simple to implement and involves only minor modifications to traditional bounding sphere hierarchies. BD trees exploit the fact that many fast deformable models integrate dynamics using efficient reduced coordinate shape representations. For example, the dynamics of this plastic chair are well approximated by the linear superposition of 10 mode shapes, the amplitudes of which are the reduced modal coordinates. Integrating the reduced coordinate dynamics is fast, and rendering deformed shapes can be hardware accelerated, so collision processing is the major CPU bottleneck. A common approach to deformable collision detection involves updating a layered bounding volume hierarchy every time an object deforms, at cost linear in the number of bounding spheres. This bridge model hierarchy has approximately 500,000 spheres, and the hierarchical update can require almost a whole second each time step. As observed here, layered hierarchies can also have loose-fitting spheres. Here, redder colors indicate looser fits. BD trees, on the other hand, bound deformed geometry within each sphere using the triangle inequality. This results in a conservative bound parameterized by the reduced deformation coordinates. Although BD tree spheres bound deformed geometry conservatively, they still form an effective bounding hierarchy, and the undeformed hierarchy wraps the geometry tightly. The key benefit of BD trees is that bounding spheres can be updated after deformation in any order, and at a cost independent of the geometric complexity of the model. The sphere update cost can be as low as 1 multiplication and addition per sphere, and at most linear in the number of reduced deformation coordinates. In our Java implementation, the worst case cost of each sphere update is about 3/4 of a microsecond for the bridge or chair model. By updating spheres only when needed during tree traversal, updating costs are limited to the number of spheres actually queried, and are thus output sensitive. Since most scenes have relatively few triangles in contact, output-sensitive BD trees can result in substantial savings. For example, a ball thrown at a curtain only hits a small portion of the curtain during a fraction of this 110-frame compressed animation. The mean per-frame processing cost for BD trees is only 22 microseconds, whereas updating a layered hierarchy each frame involves tens of milliseconds. Because BD trees are output-sensitive, collisions in complex scenes can be resolved at modest costs. For example, collisions between approximately 12,000 deformable fish totaling 300 million triangles and a complex bridge superstructure can be resolved at about the cost of rendering. By synthesizing deformations in Vertex program hardware, the CPU can focus on collision processing. Root BD tree spheres can be used for view frustum culling, thus avoiding the cost of actually rendering and deforming off-screen geometry. By processing only a small fraction of each chair's BD tree spheres, possibly up to a fixed traversal depth, collision processing can be dramatically accelerated for deformable models. Finally, this simulation of 3601 plastic chairs involves 64 million deforming triangles. The mean collision processing cost per time step is about 2.1 seconds, similar to the mean per frame cost of OpenGL rendering. Although this 25,000 time step simulation involves approximately 1.6 billion sphere collision events, the total simulation time is only 15 hours in Java. For comparison, post-deformation updating of layered hierarchies for 3601 chairs would have alone required nearly 2 months. Finally, we ran a rigid BD tree simulation. Although the deformable case has 500 million more collisions, the deformable collision processing cost is only twice that of the rigid case.